So now let's carry on with our discussion of EIGRP. We're going to get a little more in-depth of the nuts and bolts of the protocol and see how it chooses its routes and how it populates the routing table. So EIGRP uses a composite metric that is generated by using a mathematical formula. Now this composite metric is not too awfully complex, but it is different than the metrics that are calculated by other routing protocols, obviously, or why would you have a different routing protocol if it just computed the metric the same way? Now this composite metric has several multipliers known as k-values. You remember in our overview we talked about k-values. Here's where we find out what the k-values actually are. Now there are 5 k-values, and a lot of people equate the k-values with components of the metric calculation, i.e. some people say, well, k1 is bandwidth and k2 is load, etc. But that's not the case. When you see the formula, it'll be obvious that that's not the case, but you still run across some people that say, oh, k1 is the bandwidth. And speaking of the formula, here is that formula, and that's a pretty complex formula when you first look at it. However, it's simplified by the fact that the defaults for k1 and k3 are 1, and k2, k4, and k5 are 0. So that cuts out a lot of the formula, and it basically reduces the formula to this. 256 times 10 to the 7th divided by the minimum bandwidth across the path to the subnet, plus the sum of all the delays divided by 10. Your teacher always told you to study math, and now you're having to use it. The fact that this default metric formula is rather simple means that you can actually figure out what the metric should be based upon your knowledge of the network topology. So if EIGRP is not acting like you'd expect it to, then you can run your own calculations and figure out, oh, well, this is why this bandwidth on this interface is set wrong, and so that's why it's saying that this route is higher cost or lower cost. Now, like the link state routing protocols, the router runs this EIGRP metric calculation for every route that's advertised to it. And to be honest, there are actually 2 metrics for each path to a given destination, and the fact that there are 2 metrics is what allows EIGRP to converge very, very quickly, much quicker than any other distance vector routing protocol. The first is the reported distance, and the reported distance is the metric for a given route that is calculated on a neighbor router and then is advertised to me in an EIGRP update. So that's basically, for this particular route, how far away does that router over there think it is? We also have the feasible distance. The feasible distance is the metric that I calculate locally. Now in EIGRP terminology, the route with the best feasible distance is called the successor route, and that is the route that's installed in the EIGRP routing table and eventually makes it into the router's routing table. Now, routes with higher feasible distances can be stored in the EIGRP route table as feasible successor routes and can be used immediately in case that main successor route fails. And basically, the rule for feasible successor routes is if a non-successor route's reported distance is less than my feasible distance, then it is a feasible successor. And I know you're looking at this saying, I thought you said this was simpler than OSPF. Well, it really is. And let's go to the diagram and we'll see exactly why that's the case. So we have 2 subnets here, subnet P and subnet Q. We're going to look at this network from the perspective of router 5 and see if we can determine what router 5's routing table should look like. So the router 5 computes the feasible distances for each of its neighbors. So through router 1, the feasible distance is 24,000, and these route numbers generally don't come up to be this nice round number. When we actually put this in the lab, you'll see that these metrics, while they are huge like this, they don't ever come out to be round numbers unless it's just a fluke. So router 5 feasible distances through router 1 is 24,000. Through router 2 is 21,500, and through router 4 is 15,000. We also have the reported distances to subnet Q. Router 1 reports that my feasible distance is 18,000. Router 2 reports that my feasible distance is 14,000. Router 4 reports that my feasible distance is 10,000. So given what we know about how EIGRP computes routes, what should the route table on router 5 look like? Quite honestly, the router 5 topology table says that router 4 is the successor because router 4 has the lowest feasible distance at 15,000. However, we do have another router whose reported distance is less than my feasible distance, but it's still not the lowest, and that is router 2. So the topology table for subnet Q on router 5 says that router 4 is the successor. That's the route I'm going to take because that's the quickest way to get to subnet Q. Router 2 is the feasible successor. If router 4 fails, I can immediately start using router 2. Now that doesn't mean router 1 will never be used. If one or both of these fails, then this metric calculation is rerun for subnet Q, taking into account the fact that router 2 may not be there. Then router 1 becomes the feasible successor because it's the only other route there, and at that point it may have a lower reported distance. And that pretty much sums up EIGRP in depth. Again, a lot of this will make a lot more sense in the next video when we put this in a lab. But for now, we'll pause and we'll go into the lab here in the next video.